at Tel Aviv University. She's done a lot of interesting work. Okay, it's started again.
Yeah, so it's a joint work with Shoham Feldman, who is my PhD student, co-advised with Muli Sagiv, and this is basically everything that I'm going to talk about is part of his PhD thesis. And this is also joint work with Neil Immerman, Muli Sagiv, and James Wilcox. And most of the slides are taken and or abused from Shoham. Okay, so stat-based invariant inference. So I guess I don't have to say much about that. We all know how successful stat solvers are these days, and as a result, we also have a lot of approaches that tries to utilize them for invariant inference, for verification, basically. And this is a partial list of approaches that use stat solvers to verify a program, to infer invariance. And what we wanted to do in this work, in this set of works, is basically try to understand. So we know that these approaches are very successful in practice, but there is not much theoretical understanding of why they work. And this is what we wanted to tackle, basically. Try to understand why they succeed, why do they fail, and ultimately the goal is, of course, to be able to improve them if we actually understand what makes them work well. And the perspective that we took was basically through the lens of exact concept learning with queries. And I must say, so this is, I say learning, but this is about classical learning. So there will be no neural networks in this talk. And then we had a series of papers where we investigated these questions. And in this talk, I'm mostly going to talk about the first two. So let's start with some background about what is the context where we are interested in invariant inference. So basically, the context is that basically verifying safety of transition systems. And so what do I mean? So in the safety verification problem, we are given a transition system, which consists of some definition of initial state. So for example, here I have one initial, so the state here consists of a vector of n Boolean variables, and the initial state is just the state where all of them are 0. And then we also have a description of the transition relation, the steps that the system can make. So here, for example, what happens in every step is that we take these n bits that represent some number in binary, and we increment this number by some even number. So we guess some y1 to yn, and we increment the x1 to xn by 2 times this number modulo 2 to the n. So this represents a step of the system. Just take this counter, let's call it, and increment it by some even number. And when we have the initial states and the transition relation, this defines a set of reachable states, the state that we can reach by executing steps of the transition relation. And in safety verification, we also have a description of bad states, bad behaviors. For example, here, let's say that the bad behavior that I want to make sure doesn't happen is that we get to a state where the counter has value 11111. And so the goal of safety verification is to make sure that none of the reachable states is bad. Starting from init and executing steps of the system, we cannot get to a bad state. And here, clearly, it's very easy for us to see that this is the case because the counter always remains even. So we cannot get to a state where the last bit is 1. But then the question is how to do it automatically. And then a prominent way in which safety is being verified is by inferring an inductive invariant. And an inductive invariant is just a set, or we think about everything as formula. So it's basically a formula that separates the initial states from the bad states, and it has to be closed under the transitions of the system. So it has to satisfy three conditions. The initiation, which means that it has to include the initial state. Safety means that it has to be disjoint from the bad states. And then consecution or inductiveness means that if we start from a state that satisfies this invariant, we cannot, and take a step of the system, we cannot reach a state that doesn't satisfy the invariant. So we have to stay inside. And the reason why such an inductive invariant really helps us to verify safety is that if an invariant satisfies initiation and consecution, then it necessarily includes a set of reachable states, because the set of reachable states is the smallest set that includes initial states and is closed under steps of the transition relation. So it includes a set of reachable states, and therefore, together with the safety property, the disjointness from bad, we know that the system is safe. Okay, so I assume that this is not the first time you heard about inductive invariants, but if there are questions, please feel free to interrupt and ask. Okay, and let me continue with the example and illustrate this concept of an inductive invariant. So, for example, here we wanted to establish that we never reach a state where all the bits are 1, and we could take this basically saying that this is not the case as our candidate inductive invariant. So I can try to think of my inductive invariant as saying that the bits are never 1, 1, 1, 1. But if we do that, we can actually see that this is not an inductive invariant. It is an invariant. It is true in the system in all the reachable states, but it's not inductive because we can start, for example, from a state where all the bits are 0 except for the last one, and then we can increment it by some even number and get to the state that where all the bits are 1. Okay, so it's not inductive, but there is another inductive invariant that we can use here. For example, we can say that the least significant bit is not 1, and this is an inductive invariant. So if we take this, we can see that it includes the initial state. We can see that it is disjoint from the bad state, and this is preserved by every step, because if the least significant bit is 1 and we add some even number, the least significant bit remains. So if the least significant bit is not 1, 0, and we add an even number, we remain with an even number. Okay, so this is an inductive invariant. And in invariant inference, our goal is basically to find such an inductive invariant automatically in order to verify safety. And in SAT-based invariant inference, which is what I want to talk about, the idea is to use a SAT solver in order to find an inductive invariant automatically.
So I have a question.
Yeah.
So are we talking about finite state systems?
Yes, so great question. So yes, in this work, we focused on systems where the state is just a set of Boolean variables. So we have finite state systems. Yeah.
Okay, thank you.
Thanks for the question. I was supposed to remember, and now I did. Okay. Okay, so just to give a simple example of how a SAT solver can help us in the task of at least verifying that a candidate invariant is indeed inductive, then really the setting that we are going to look at is, well, the initial states, the bad states, the transition relation, all of these are given as propositional formulas. So we have a set of Boolean variables, and these are formulas over them. Delta, the transition relation formula, is a formula over 2 copies of the variables. The unprimed copy represents the current state, and the primed copy represents a state after a transition, the next state. And then, so if we have this, and we also have some candidate inductive invariant that is also a formula over these variables, then we can check all the requirements of an inductive invariant, initiation, safety, and consecution, just using a SAT solver. For example, initiation said that the initial state have to be a subset of the invariant, and this is just saying that the set of states satisfying init, but not satisfying the negation of the invariant is empty, which is just saying that this formula is unsatisfied. Okay, and the same for all the other requirement. So at least we can see that a SAT solver can help us check if a given candidate is inductive. Okay, so this is some background about SAT-based invariant inference. And now, now I see that this is hiding part of the slides for me. Okay, never mind, I'll manage. Okay, and now the second part, like I said, I want to investigate SAT-based invariant inference from the perspective of exact concept learning with queries. So what do I mean by that? So in exact concept learning with queries, we have our goal is to learn some unknown concept and phi, and we can think of this concept in our case just as a formula. So we are trying to learn some formula phi, and the way to do it is that the learning algorithm, who is supposed to learn this formula, can interact with an oracle or a teacher by asking certain kinds of questions and receiving answers. So for example, the learning algorithm can come up with some candidate psi1 and send it to the oracle and ask, is psi1 the concept? Is it phi? And then the oracle has to answer correctly, either say yes, it is, or say no. And if it says no, it will also provide a counterexample, some state that satisfies phi but not psi1, or the other way around. And again, then the learning algorithm can provide another candidate, the oracle has to respond, and so on. These kind of queries are called equivalence queries. These are the queries where we provide a candidate and the answer is whether this is the correct answer and otherwise a counterexample. But there are also other queries. Another common kind of queries is membership queries. And in membership queries, the learning algorithm just takes a state, an evaluation of the variable, and asks the oracle whether this state satisfies phi. And in this case, the oracle just says yes or no. And this process goes on, and the learning algorithm keeps asking questions until it really finds the correct concept formula phi. Okay, so this is exact concept learning with queries. Okay, so now when I start from this and I want to go back to SAT-based invariant inference, and I want to think about it as some sort of learning with queries, then there is a clear similarity. So before we talked about in learning, we talked about trying to learn some concept. So here the concept that we are trying to learn is just an inductive invariant. And the learning algorithm is just going to be the inference algorithm that is supposed to infer this inductive invariant. Our oracle is going to be the SAT solver. The inference algorithm asks the SAT solver's satisfiability questions, and the SAT solver responds. But then, of course, there is also a very important difference, and the difference is that unlike the setting of learning, where we assume that the oracle actually knows the concept that we are trying to learn, when we are thinking about the SAT solver, we don't want to assume that the SAT solver knows the inductive invariant. So this is a very important difference. And really, in order to capture the fact that we are thinking about SAT-based algorithm, because we cannot assume that the SAT solver knows the invariant, what we do is we say that, okay, we are going to look at inference algorithms that don't know the transition relation. They cannot access the transition relation. The only way to access the transition relation is by asking the SAT solver. So this is the model that we consider. The transition relation is only known to the SAT solver. So instead of knowing the invariant, the inductive invariant, it knows the transition relation, and it can answer questions about the transition relation. Okay, and again, the goal is for the inference algorithm to interact with the SAT solver, ask all sorts of questions about basically the transition relation, and ultimately infer an inductive invariant. And then the next question that comes up is, okay, but what kind of SAT queries is the inference algorithm allowed to ask? And
So
this
question again.
Yeah.
What is the intuition behind pushing delta into the oracle, and why not letting the inference algorithm?
I can't hear very well. Can you maybe speak up a bit? Or?
Yes. So I'm saying, what is the intuition behind pushing the delta, the transition relation, into the oracle and not the inference algorithm itself?
So what we wanted to do here is really understand basically what makes a SAT-based algorithm SAT-based. So most SAT-based algorithms that we are thinking about, algorithms like interpolation and IC3, and basically most of the list that I looked at before, they usually don't do any white box analysis of the transition relation. They don't do static analysis. They don't do anything themselves with the transition relation. All they do is ask when they want to check something, whether a candidate is inductive, or if they want to check reachability in a certain number of steps, they just take the transition relation as it is and send it to a SAT solver and let the SAT solver answer the question. So we said that we might as well think of a model, and as I will mention later, this model does capture existing algorithm. So a model where the inference algorithm just cannot use the transition relation itself. It can only do it through the SAT solver. This was basically our attempt to say what is somehow, basically, I don't know, maybe find some characteristic of existing SAT-based algorithm. Because we wanted to capture the fact that we are asking solver something. So, and we needed to assume that there is something that is known to the solver and not to the inference algorithm. And maybe I should also say in this context, and this is a bit, I will get to it later, but the kind of results that we will have will really not depend, for example, on the complexity of SAT solving. And basically, the results that we obtained are based on information. We will basically see that the inference algorithm needs to make enough queries in order to really gain information about the transition relation. Okay, so I don't know if I answered, but the short answer is that really we found that this captures really algorithms that we were interested in, and I will show some examples later. And this was basically our way to say what characterizes a SAT-based algorithm as we know it, as the kinds that we looked at.
I see. So the other option could have been that we ask the SAT solver queries like, is it the case that this invariant is inductive, this invariant doesn't intersect with?
So this is related to the question, which SAT queries? So in the next couple of slides, I will start talking about really restrictions to certain kinds of queries that we can ask the solver. But the assumption that the inference algorithm itself doesn't know the transition relation, this will remain. And it's important because if it knows it, then it actually can answer any question that it asks the SAT solver. It could have answered by itself, just by doing
at the end, at the end, the problem is well-defined and decidable. So I understand what you're trying to say in the later part. Okay, so let's, I think, move on and maybe my question will be answered.
Sharon, I had a quick question as well. So the transition relations are assumed to be all deterministic?
No. It's a relation.
Okay, so in the previous example, I could have had, I have a vector of n bits and I flip n coins, and that could be my output state. Okay.
Yeah. I mean, so we don't talk about probabilities. So for me, it's just you guess. Okay, no. Yeah, so there is no probability here, but yeah, it could be completely non-deterministic. And the example was we incremented the counter by some even number, could be n.
Okay, understood. Thanks.
Okay, so basically, this is now what I'm going to do next. So we talked a bit about SAT-based invariant inference, a bit about exact concept learning. And like I said, I want to look at SAT-based invariant inference by somehow comparing it to exact concept learning. And what we will do is we are going to define basically two query models for invariant inference. So the question from before, which SAT queries, we will have two answers to that, two models that we consider. For each of these models, we will provide some complexity upper and lower bounds on the number of queries that are needed in order to learn an invariant. And from this complexity result, we will actually be able to see that invariant inference in this model from queries is harder than exact concept learning. So this is all quite negative because actually, our goal initially was to be able to take advantage of all the literature on exact concept learning in order to maybe come up with new algorithms for invariant inference and maybe implement exact concept learning algorithms for invariant inference. So this seems quite negative if the problem is harder, but then we also have results show that under certain conditions, we can get complexity results from learning, from exact concept learning, and somehow get the same results for invariant inference, and actually also get new algorithms by adopting existing learning algorithms. So I hope I will be able to talk about that as well. Let's see how much time we have. Okay, but the first thing, we will just start by defining query models for invariant inference as learning. So I go back to this picture. Let me just try to get rid of this. Okay. So the first model that we consider is we call it the inductiveness query model, and this is exactly the example that was given before, basically. In this model, the kind of queries that the inference algorithm can pose to the SAT solver, to the learner, are inductiveness queries, which means that it would provide some formula, alpha I, and ask if alpha I is inductive, which means if we start from alpha I and take a step, is it guaranteed that we end up back in alpha I? And it's easy to see that this can be implemented by a satisfiability check. So this is written here, okay? And this is the first model. This is the kind of question that the inference algorithm can ask. And then the SAT solver, the inductiveness query oracle, will answer yes if alpha is inductive, and otherwise it will provide a counterexample. But note that here a counterexample is not just a state that distinguishes the invariant from alpha I, because we don't know basically to give such a state, not in an easy way at least. So a counterexample here is going to be a counterexample to induction. This is not a state, but a pair of states, sigma and sigma prime, such that sigma satisfies alpha I, but sigma tag does not, and there is a transition between them. Okay, so this is the first model. And this model may look familiar because this model basically captures exactly algorithms in the ICE framework that was proposed way before. So in the ICE framework, the learner is supposed to learn a candidate inductive invariant from examples. And there are three kinds of examples. Positive examples, these are states that are known to satisfy the invariant. And for example, this could be generated from the initial state or doing some bounded reachability. Then there are negative examples, examples that are known to not satisfy the invariant. And for example, this could be bad states. Then we know that bad states definitely do not satisfy the invariant. And the new kind of examples are implication examples. And these are pairs of states, sigma and sigma prime, such that if sigma satisfies the invariant, then sigma prime also has to satisfy the invariant. Okay, so this is an implication, and such implication examples can exactly be generated from CTIs. The CTI is a transition of delta, and then of course, if the pre-state of a transition satisfies the invariant, in order to have inductiveness, we have to have the sigma prime also satisfies it. Okay, so basically, algorithms in the ICE framework we can think of them as algorithms in the inductiveness query model. Okay, so this was one model, and then we can ask ourselves, right? So this is one possible model. Is it sufficient to capture existing SAT-based algorithms that we are interested in? So we see that it captured algorithms in the ICE framework, but what about other algorithms like interpolation and IC3 that we were really interested in? So let me now give some background about interpolation-based inference, because that's basically what I'm going to talk about most in the rest of the talk. So interpolation-based inference was proposed by Macmillan in CARV 2003. And the idea here, so again, we are trying to infer some inductive invariant. And the idea here is that at any point we have some candidate inductive invariant I. Initially, we just take the initial states and we check if is it inductive. If it's initial state, usually it will not be inductive. And when it's not inductive, we try to extend it in order to find a new candidate. And the way in which it is done is we do some bounded reachability check, bounded model checking of k+1 steps, checking if from our candidate I, init in this case, we can reach a bed state in k+1 steps of the transition relation. If we can, if this bounded model checking query is sat, then we found a counterexample and there is no hope to find an inductive invariant, we are done. But if it is unsatisfiable, then we are trying to use this result in order to extend our candidate inductive invariant. And the way to do it, so if the k+1 reachability query is unsat, this means that if we think of the post image of I, we know that in k steps, this doesn't reach a bed state. Okay, we know that this bounded model checking query is also unsat. And the idea is in interpolation is now to extend our candidate I with some generalization of the post image of I, an interpolant that again generalizes the post image in a way that the interpolant is still doesn't reach a bed state in k steps. So we compute such an interpolant, we extend our candidate I with this interpolant. This is our new candidate I. Again, we ask, is it inductive? If it is, we are done. If it is not inductive, then again, we do the same thing. We check k+1 reachability to the bed states. Note that here, if we see that if the query is satisfiable, if we do find a trace from I to bed, it doesn't mean that we found a counterexample because this I now contains states that are not necessarily reachable. And what happens here is that we just increase k. So k is a parameter here, and I'm not going to talk about it a lot. For me, I will usually talk about some fixed k, but I just wanted to mention it here. Okay, but if the query is unsatisfiable, again, we generate an interpolant and we continue until we find an inductive, until our I, the disjunction of all these interpolants, is inductive. Okay, and in the original work by Macmillan, the way in which the interpolant was computed was based on the unsatisfiability proof generated by the solver for this bounded model checking query. But in our work, we looked at a variant of this algorithm that was proposed later, where the computation of the interpolant is closer to the kind of generalization that is done in PDR. So let me now explain this, and I'll use the example to explain it. So here, when we try to compute the interpolant, the generalization of the post image of I, this delta of I, then instead of trying to compute an interpolant for this set as a whole, what we do is we do it step by step. So we take some state, we sample some state from the post image of I, from this delta I. And for example, how can we find such a state? We can, if we ask if this I is inductive and the answer is not, then taking the post image of a CTI is exactly a state in the, sorry, taking the post state of the CTI is exactly a state in the post image of I. So we take such a state, and then, so for example, here, this could be our state. This is a state that is reachable in one step from init. And then we are going to extend our candidate invariant by a cube that represents this state. But before we do it, we try to generalize, just like we wanted to generalize with Macmillan's idea. So here, the way we generalize is by trying to drop literals as long as this bounded model checking query remains unsat. So for example, we can try to drop this literal, x1 equals 0. And if we do that, we can see that from the cube that remains, it is still impossible to reach a bed state in k steps. Doesn't matter what k is in this specific case. So we really drop the literal and we are happy. Again, if we try, after we drop this, we now try to drop x2 equals 1, and we will also succeed because this remains unsat. But if, for example, we try to drop this literal, saying that the least significant bit is 0, then when we drop this, now we can get to a bad state in actually one step. So we see that we cannot do this generalization, so we don't do it. And if we continue in this way, in this particular example, starting from this state in the post image, we will be able to drop all the literals here until we have just the literal xn equals 0. And in this specific case, this is already the inductive invariant. So of course, this is a very simple example, but you see, we just took one state from the post image, we generalized by dropping literals, we added this cube as a disjunction in the invariant, and in this case, it's already the inductive invariant. Okay, more generally, what let's look at the pseudocode of the algorithm, which we call ITPK because of the k, the parameter k. What is going on is that we have our candidate here, it's initialized to false, doesn't really matter. And then as long as our inductive invariant is not inductive, we take a counterexample to inductive, we take the post state, and we add it to the candidate invariant after generalizing it. And the generalization is just done by dropping literals. As long as the bounded model checking query that makes sure that we cannot get to bed in case steps remains unsolved. And in this way, what happens is that eventually we infer an invariant in DNS, where each term or cube in the DNS is just the result of generalizing some post state of some CTI. Okay, is the algorithm clear? Okay, I assume yes.
So Sharon, in the last, maybe just to understand the algorithm in the last example.
Yeah.
How did, so you took the one-step state, that's the delta of I.
Yeah, this was this. Yeah, so this could be, this is of course not the only state, right? Because it's some state that I can reach in one step from 0, 0, 0, 0, which is basically every even number. So this is just an example, and it doesn't matter in this case, it doesn't really matter which state I would have chosen. Any state, and basically taking any even number would have let me generalize all the literals, and I would have remained just with the least significant bit being 0 in this specific simple example.
Okay, so how did you generalize this one? So the point was 0.
So when I drop 0, for example, I drop 0. So now instead of describing just this state, now I have two states in mind. The one where the most significant bit, is 1, and the other that is exactly sigma 1. But both of them cannot reach a bad state in any number of steps. This is why my bounded model checking query is unsolved. Because both cases, even when I drop this literal, it basically means that now I consider two states that differ in this first bit, and both of them cannot reach a bad state in any number of steps. So because of this case, I really drop the literal, I don't bring it back, okay? Because my generalization succeeded. It's still a formula that doesn't reach a bad state. And then I do it for every bit. I mean, so I drop the first one, and afterwards I drop this one. So now I actually consider 4 states, and so on.
Yes. So
Okay,
finally,
so I have
yeah, go ahead.
So my question is, this seems to be specific. So the order in which you're dropping the bits, would that also matter?
Yes.
Okay. Okay.
Yes, it can in general. Yes, definitely, but I'm not. Yeah, this was just a simple example to illustrate the algorithm. So
Okay. Yeah.
in general, it can be important. Okay. Okay. So this was the pseudocode and the final invariant that we get in DNS. Okay. And now, hopefully, if the algorithm is clear, what I want to do is go back basically to the inductiveness query model and ask whether we can really capture this algorithm, which is a SAT-based algorithm, in this model. And if we look at that, so one thing, okay, this is a reminder of the inductiveness query model. This is the kind of queries that we can ask, inductiveness queries. And So if we look at the queries that we make here to the SAT solver, the first one is clearly an inductiveness check. So yeah, of course, this we can model in our inductiveness query model. But the second one, the bounded model checking query, not clear, right? It doesn't look like an inductiveness check, right? So this not immediately. So, okay, so what we did, we now defined another query model that will allow us to ask this question, and then we will be able to compare these models and ask ourselves, do we really need to generalize and so on? Do we really need the second model, basically? Okay, but first, so let me now define the whole query model, the second model that we consider. And in the whole query model, so the story is the same. The difference is the kind of queries that we can ask. And here, each query basically consists of two formulas, a precondition alpha I and a postcondition beta I. And the question is whether, the question is basically a whole triple, whether when we start from alpha I and we make k steps of the transition relation, are we guaranteed to end up in beta I? Okay. And this can again be implemented using a SAT solver just by a bounded model checking query of k steps, checking whether this is answered. So this is the second model. And like before, so if the whole query, if the whole triple is correct, then the oracle will just say yes, but otherwise it will provide a counterexample. And here, so before in the inductiveness model, counterexample was a pair of states. Here, a counterexample would be basically a trace that starts from alpha I, ends in not beta I, and consists of k transitions of the system. Okay?
So one more question. So I know you're treating the oracle as a literal oracle, but it seems that if you do delta k, then actually even constructing the SAT query may be more expensive.
Are you asking about the k?
Yeah.
Yeah, so the k is actually not really important. This is just because I try to combine some results. So for some of the results, actually k is not important. When I will show that there is a difference between the inductiveness query model and the whole query model, k will not be important. I will just use k equal 1. Okay, but the reason why it is k is because we do want to capture interpolation, the general case of interpolation, where we do use bounded model checking queries with a larger k, not just one.
Okay.
So it's like a mixture of things, but I will mention this point about the k equals 1 when it's when it is really the case.
Okay, thank you.
Okay, and now the claim is that this model can model several interesting algorithms. So for example, let's look first at the interpolation-based algorithm that I mentioned. So now I think it's easy to see that we can capture it. The first query is just inductiveness, which is a special case of a whole triple, basically. And the second query, the bounded model checking query, is exactly what we now can check. If we want to check that from sigma tag we cannot reach that, this is just like checking the whole triple, sigma prime, and post condition not bad. Okay, so it clearly captures this algorithm, and I will not show it here, but we can also capture IC3 PDR in this model. Okay, so these are the two models that we consider. And now going to the next item, now I want to talk a bit about the complexity, basically how many queries we need in order to infer invariance in each of these models. Okay, so and the first result is just giving a lower bound on the number of queries that we need in the whole query model. The whole query model is the more powerful one that can ask about whole triples and can even have this k that is a parameter. And the theorem says that in this rich query model, every algorithm requires at least an exponential number of queries to infer invariance in DNF, and even to infer short invariants. So these are invariants that are that have a polynomial length. And I just want to say that so we were mostly focused on inferring short invariants, because if the invariants, if we are looking at a system that has only a very long invariance, there is no much hope to infer these quickly, okay, or at least to write the invariant would take a lot of time. So we are thinking about the case where there is a short invariant, and we ask ourselves the question, how expensive is it to infer this short invariant? And here we say that in the whole query algorithm, we need at least an exponential number of queries to infer even these short invariants in DNS. And its exponential, this n, is the number of variables, propositional Boolean variables. And I will not always mention this in the rest of the talk, but I will always talk about short invariants. I will always talk about the invariants of polynomial length. Okay, and again, to emphasize some things about this theorem. So this theorem says that we need this number of queries, and this is even without limiting the computational power of the inference algorithm. The inference algorithm can even solve compute uncomputable functions. Okay, it will not help it, and this is what I mentioned before. It uses basically the oracle to gain information. So this bound is basically an information bound. And it's really unconditional on any computational power of the inference algorithm. It's basically the number of queries that are required in the worst case. I'll just say a few words about the proof. So the idea of the proof, the very rough idea, is that we show that if we take any inference algorithm that requires less queries, then we can construct two transition relations. One that has a short inductive invariant with n terms or cubes in DNS, another that doesn't. Actually, the other one is not even safe, so it doesn't have any inductive invariant, but we can construct these delta 1 and delta 2 such that all the answers of the whole query oracle are the same when the algorithm runs on both deltas. The answers are the same. Okay, I will not get into more details, I think.
So the proof sketch that you show doesn't even require the assumption of DNF.
So the delta 1 that we no, it does. The delta 1 that we construct that has an inductive invariant, the invariant will be in DNS and not simpler. Maybe okay. I don't understand. Oh, if I don't restrict it, yes, to a more general class, yeah, the proof still applies. But I cannot say, like, for example, it doesn't apply if I want to think of a simpler invariants, then it doesn't apply. Yeah. Okay, and actually I do have one, so I'll skip the rest of the details, but I do want to say something. Actually, in the proof, what we see is that the inductive invariant that exists for the delta 1 that does have one is actually monotone. Monotone means that all the propositions appear only positively, and this gives us actually a stronger corollary even. And this corollary says that every whole query algorithm requires an exponential number of queries to infer even short monotone DNF invariants. So these are even simpler invariants, just monotone, a smaller class. And even for that class, it is already required to have an exponential number of queries. So this is basically the first theorem, and this is a lower bound for the more general model. So of course, it also applies to the inductiveness query model that is simple. The second theorem that we're really excited about is a theorem that shows that there is actually a gap between the whole query model and the inductiveness query model. And this theorem says that there exists some class of transition systems for which there exists a whole query algorithm that can infer invariants for these transition systems with a polynomial number of queries. And you see here, this algorithm will only use k equals 1 in the delta k, so it's just delta. So the difference doesn't come from there. So there exists a whole query algorithm that is basically efficient, but every inductiveness query algorithm will require an exponential number of queries in the worst case. Okay, and I will give again some ideas about the proof. So let me tell you what this class of transition systems is. So the class of transition system is the set of maximal transition systems for monotone DNF with n queues. So monotone DNF, we already mentioned. Monotone just means that all the propositions appear positively. This is an example of a monotone DNF formula. And a maximal transition system for a formula is basically a transition system that includes all the transitions that do not violate inductiveness of this formula phi. Okay, so we will have all the transitions from every state that satisfies P to every state that satisfies it, transitions from states that don't satisfy P to states that don't satisfy Phi, transitions from states that don't satisfy Phi to states that satisfy Phi. The only transitions that we will not have are transitions from inside Phi to outside Phi. Okay, all the other transitions are there in the transition system. And the claim is that for such transition systems for Phi that is monotone DNF, if we take this class of systems, we have this gap. Okay, so now let me give you an idea about the upper bound first and then the lower bound. Okay, so the upper bound says that for this class, there exists the whole query algorithm that is efficient. And actually, we already saw the algorithm. So the previous interpolation-based algorithm that I showed, the claim is that this algorithm will infer the invariant for such a transition system in a polynomial number of queries. And why? So first, let's look at the number of queries. So the claim is that in this outer while loop, every iteration will just learn one cube term from the invariant. And since we took a system that where the invariants have n cubes, this means that we'll have n iteration of this loop. And in each iteration, what we do is just try to drop literals one after the other. So each iteration has n BMC queries. So altogether, we get a quadratic number of queries. Okay. So what remains is to really convince you that in each iteration of the while loop, we will really learn one cube from the DNF invariant. Okay, and why is that? Okay, so first, let's notice that when we do this, when we try to drop a literal and we check reachability, whether after dropping a literal, the cube that we get can reach bed, and we make sure that it cannot reach bed, this already ensures that the sigma prime after dropping a literal is still included in phi, because we know that every state that is not included in phi can reach bed in one step. Every state in this area of not phi can reach bed in one step. So this check basically ensures that our generalization always keeps us underneath phi. We never cross the border, never include a state that is not in phi. This is one thing. And the fact that we continue to drop literals as long as this is the case, so basically sigma prime is an implicant of phi. And the fact that we drop literals as long as this is the case means that this is a minimal consequence, or basically a prime implicant of phi. And because we took formulas that are monotone, so for a monotone formula, we have the property that every prime implicant is actually a cube in the formula. It's really a cube that is present in the formula. So this ensures that in this generalization step, in each iteration, we get a prime implicant, which is a cube in the invariant. Okay, is that clear? Okay, so this explains the upper bound. And just, as I said, and just note that in this algorithm, we really did use a query that at least doesn't look like inductiveness. Okay, so we utilize the fact that we are in the whole query model. This was the upper bound. Now to complete the gap, let's look at the lower bound. The lower bound says that if we look at an inductiveness query algorithm, then it doesn't matter which one we take, we will have a lower bound of an exponential number of queries. And here the proof is that when we look at the inductiveness query model, if we get a yes answer, then we are done because we found an inductive invariant. So here we only care about the no answers and the counterexamples. But now if we think about some system that has phi as an invariant and compare the run of an algorithm on this system to the run on the maximal system for the same phi, we can see that any answer that the oracle can give in this system, it can also give when it runs on the maximal system, because in the maximal system, we just add a transition. So any transition that was here, was a CTI here, is also a CTI here. And this tells us that basically when we look at the inductiveness query model, trying to infer invariance for maximal systems is at least as difficult as trying to infer invariance for general system. So the maximality doesn't help us in this model. And for general systems, we just saw before that inferring monotone DNF invariance for general systems requires an exponential number of queries. So altogether, we get that in the inductiveness query model, we need an exponential number of queries, even when we try to infer invariance for maximal systems for this class. Okay, so this gives us the proof of this gap. And I showed the upper bound using an interpolation-based algorithm, but actually we can do a very similar proof using a simple case of IC3 PDR. And this really shows that there is a gap between basically these two models, and specifically it shows that IC3 is not, so remember that I said that the inductiveness query model is basically the ICE framework. So this shows that IC3 is not, cannot really be captured by the ICE framework. And actually in a previous paper a few years ago, we had a paper where we did try to show that IC3 is some instance of ICE, and we really failed, and we had to extend the kind of queries that are allowed. And now in this result, we basically gave the formal justification. We basically proved that it's not possible to describe IC3 as an instance of ICE, because IC3 really is, at least in this sense, it's more powerful. Okay, so this was about some complexity bounds. Wow, and I see that I don't have much time left, so I just I guess I'll skip the interesting part, so you will have to remain curious, but I will at least derive some conclusion about the relation to concept learning. So to summarize what we basically said so far, we had two query models, the inductiveness query model, the Hoare query model, and we also considered two families of transition systems, the general, where we didn't have any restriction, and we also considered these maximal transition systems. And we saw that when we look at the Hoare query model and we try to infer invariance for maximal transition system, monotone invariance for maximal transition system, then we have a polynomial invariant, an algorithm that requires a polynomial number of queries, but in all other cases, we needed an exponential number of queries. This is about invariant inference. And now, if we look at what is known in the literature of exact concept learning about learning monotone DNF formulas, then if we look at a model that only has equivalence queries, there is a sub-exponential algorithm. And if we allow both equivalence queries and membership queries, there is a polynomial algorithm. So now we can look at the two things somehow in comparison. And inductiveness queries seem very similar to equivalence queries. In both cases, we provide some candidate and we ask, is it this? And we get some counterexample. The difference is that when we look at equivalence queries in the learning context, the counterexample is either a positive or a negative example, whereas in the inductiveness query model, it's a pair of states, it's an implication. And basically, this gap in the complexities show that this difference in the kind of counterexamples is really important, is really crucial. And basically, this shows that learning from counterexamples to induction, as opposed to just negative and positive examples, is really harder. And again, this was an insight that was mentioned by the authors of the ICE framework, sort of informally. And now we basically have a formal justification to it. Okay, and another conclusion that we can draw, if we look at the most general case of the Hoare query model, and the complexity for inferring invariant for general systems and compare it to this entry where we allow equivalence and membership queries in learning, again, we see a gap. And this again tells us that in general, even in the richer Hoare query model, we cannot implement equivalence and membership queries. we cannot implement a teacher for such queries in the general case. Okay, so these are basically a bit negative results, and I don't have time, so I guess I will skip the rest of the last part, but I will say that it exists. And then the last part is basically that even though in general we have these negative results, we did identify some sufficient conditions that do allow us to implement basically equivalence and membership queries, and then take an exact learning algorithm and transform it into an invariant inference algorithm that has the same complexity. So this is the last part. And I think, I mean, I assume that I have to finish, right? I mean.
Yeah, maybe how much time? Maybe another 5 minutes or so you could.
Okay, so let's see what I can say in 5 minutes about that. Let's see. Okay, maybe I will just give at least an idea. So, okay, basically, how and when can we take a learning algorithm and transform it into an inference algorithm? In order to do that, we need to somehow implement the teacher. And this is difficult because we don't know the invariant. So we need to answer now questions about the invariant, which we don't know, the oracle doesn't know. And we need to somehow do it. So what I want to show is that it seems undoable, but actually we sort of did it already. So what I have here on the slide is an algorithm for learning from the exact learning literature for learning DNF formulas. And don't even bother to look at the details, just look at the fact that if I take this equivalence query and replace it by an inductiveness query, and this membership query I just replaced by this, then I get exactly, basically, the interpolation-based algorithm that we saw before. So basically, we can understand the interpolation-based algorithm as some implementation of this algorithm for learning DNF formulas. And this means that if we have some known efficiency result for learning DNF formulas, we can deduce them also for interpolation-based algorithm. But this is also only true if the transformation that we made is correct. If it's really, if these queries in the if these subqueries really implement the queries in the learning algorithm. And what we showed is we proved the theorem that under some conditions that we call the invariant has to be k-fenced. I will not have time to explain what this means, but if the invariant is k-fenced and the algorithm's queries are of a certain shape, then we can really implement the queries of a learning algorithm and transform the algorithm into an invariant inference algorithm. This is the case really for interpolation-based algorithm. We can really get it as an implementation of the learning algorithm because the queries are of this form. And then if the invariant is k-fenced, we can also take the complexity results of the learning algorithm and basically import them to the invariant inference algorithm. We are guaranteed to have the same complexity for k-fenced invariants. And I will not have time to explain the condition, unfortunately, but I can show what we get from it. Okay, what we get from it is that if there exists a learning algorithm that can identify formulas in some concept class C efficiently using queries that are one-sided, then we can take this algorithm and we can transform it into an invariant inference algorithm that infers inductive invariants in the same class of formulas also efficiently whenever the invariant is k-fenced, which is another condition. And again, this applies specifically to the case of monotone DNF, where if we take this algorithm that I showed before, it's efficient for this class, and transforming it gives us the interpolation-based algorithm. So basically, we conclude that the interpolation-based algorithm is efficient for learning monotone DNF invariants that are k-fenced. So this is basically one conclusion. This is this theorem that the known interpolation-based algorithm is efficient for invariants that have a short monotone DNF representation and that are k-fenced. And then, so this was a known algorithm, but then we can also use the same result to take an algorithm for learning, for example, short, almost monotone DNF formulas. And with the same transformation, we get an inference algorithm for such invariants. And this was not an algorithm that was known before in the context of invariant inference. And it also has a polynomial complexity if the invariant is k-fence. And we also had some generalizations, but let me skip and just conclude. So basically, what we did here, we looked at SAT-based invariant inference, tried to compare it to exact concept learning. To do that, we first somehow introduced a model of inference that relies on queries to a SAT solver, and we consider two kinds of queries: the inductiveness queries and the Hoare queries. We developed some complexity lower and upper bounds for each of the models and showed basically that there is a gap between them. We also showed by these complexity bounds that invariant inference in general is harder than exact concept learning from queries. But we also showed that under certain conditions, we can implement learning algorithms as invariant inference algorithm and also get the same complexity results. So this is it, and then there are many questions that can come up and can be really interesting for future work. For example, I talked about we actually managed to come up with some complexity results for interpolation-based algorithm, but what about IC3 PDR? Can we somehow get a complexity result for that? I think this question came up. What is the impact of K? So we didn't really look into that. There clearly are differences. If we increase K, it should affect the power. This fence condition that I didn't have time to explain, is it really a necessary condition for the ability to implement? Maybe there are other conditions. And then, of course, also it's very interesting to see if we can take any of these ideas and apply them beyond Boolean programs, finite state programs, if we can think about transition systems that are modeled using first order logic and so on. So that's it. Thank you.
Thank you, Sharon, for that excellent talk. Are there any questions?
Any of you now, unfortunately, and I don't know how to make it come back. I hid the. How do I do it? I don't remember.
Is there there's a view button on the top right? Can you see that? I don't know whether that's there.
Yeah, so I think I made it go away somehow. I have participants, maybe. Yeah, I don't know. I can see the chat if I want. Anyway, I just can't see anyone, and I don't know how to. Yeah, but feel free to ask questions, but you have to say something because I can't see you.
Right. So are there any questions?
Yeah, so yeah, hi, I have a question, Madhukar here. So I'm not sure if I followed this remark of the impact of K, but are you trying to say that the Hoare query model for a bigger K is more powerful than one with a smaller K?
So there should be a difference. I don't know. We didn't investigate that. So like I said, for example, when we talked about the gap between inductiveness and the Hoare query model, now in any case, we just considered K equals 1.
Yeah.
And already with that, there was a gap. But we didn't really investigate the question, how much power do we gain when we allow bounded model checking with a larger horizon?
Okay, yeah, but
so
what's
I think it's interesting, but yeah, I don't know. It's not that I don't have results on that. I assume that it is important.
Okay, and what's your guess? Is it more powerful?
So the question is, I mean, is it exponentially more powerful? I don't know. I really don't know. But I do believe that there is a difference. I think that bounded model checking in general, as opposed to just one reachability step, makes a difference. That's my intuition, but I don't know. It's not founded on anything. So
yeah, sure. Thanks.
I don't know.
Thanks.
Also, Sharon, about the so this whole thing is in a Boolean program setting. I think that was one of the questions in your conclusion also. Whereas typically we are trying to find, these invariants for, integer programs and infinite state space. So what do these, do these results carry over to the setting, or?
So actually about integer programs, we thought even less. What we did try to think about was really first order without theories, like uninterpreted functions and stuff like that. But we didn't find an easy way to carry over the results. In particular, even the idea of generalizing just by dropping literals is not necessarily the best generalization scheme when you're thinking about first order logic, because then sometimes you would like to, maybe you want to take a variable and somehow split it into two variables. For example, maybe you had for all x px and you want to make it for all xy pxy. So even that idea, so we didn't manage to come up with results for first order transition systems, and we didn't really look into theories. So it was mostly in the setting of uninterpreted functions. I don't know. So yeah, it's interesting. The first thing is really to understand what is known in learning algorithms. I don't know if I don't know literature in exact learning that somehow tackles the question of learning formulas over. I don't know. I'm sure there are, but I don't know. So I guess the first question is what algorithms exist, and then whether they would carry over. Maybe we need similar conditions. I'm not sure. So I think it's really interesting to investigate, but we just haven't.
Right. Okay. Are there any more questions?
But I do want to say, so yeah, this is Boolean programs, which is somehow limited. But on the other hand, if we think about predicate abstraction, then after we apply predicate abstraction, we do have a Boolean program. So it's not that it doesn't apply at all to infinite state systems. It does apply if we use predicate abstraction, which is limited, but it's not. I mean, it's something.
Right.
Yeah.
Okay. Okay, so it looks like there are no more questions. So let's give Sharon a hand. So thank you, Sharon, again.
Thank you very much.
Thanks.
Okay, I stopped sharing. Now I can see you.
Yeah.
This was at this one click. Okay, thank you.
Yeah. Thank you all for joining. Thanks for the